Okay, so we'll continue from where we left off yesterday. I'll quickly review what we did before moving on. Okay, we pointed out that the PA kind of resides right at the antenna, right, just before the diplexer in the transmit chain, and the power level depends on what kind of application you're going to use it for. Then the PA now needs to drive 50 ohms, unlike other circuits inside the IC. The PA needs to drive 50 ohms. Okay, we wanted to have high power, good amount of gain, high efficiency, right? Those are the big things. So we started off with a common source amplifier, right? Then what happens is we started off saying, okay, common source amplifier, you need to bias it at the current source. Okay, you add the current source because you need to bias it. Okay. Next step, bias it using a PMOS transistor. If you bias it using a PMOS transistor, obviously you need to bias it using feedback, because the NMOS and PMOS cannot be biased independently. So we said, you can use feedback, negative feedback, just for bias alone. So we came up with one possible structure. Then we said there are many possible structures, but even better is to use an inverter. Use a biased inverter. Okay, so that seemed to work. It gave you some gain, GMN plus GMP times RL. Okay, it is biased somewhere around VDD by 2. That's great, but there is a problem. The linear swing you get is about VT, right, plus or minus VT. So VT is the amplitude. Peak to peak swing is 2 VT. So that is normally not good enough. You want to extract out as much swing out of the PA as possible, because you want to get as much power output as possible. So limitations, number of degrees of freedom. The only degree of freedom in this is the width of the NMOS. Everything else is fixed, right? You change the width of the NMOS, automatically bias current will be set to a new value which depends on this. WP is automatically some multiple of WN. Okay, you don't have any other degrees of freedom. It has limited bandwidth because parasitic capacitances at the output node will limit your frequency of operation. Okay, this is really not scalable. The maximum output power that you can get from this circuit is VT squared by 2 RL. Okay, basically the maximum amplitude is VT. The maximum RMS value is VT by root 2. So VT by root 2, the whole squared, over into times 1 over RL will give you the power. Okay, for typical values of VT, you can probably get a few milliwatts. Okay, not much more than that. Of course, the saturated power is much higher than this, because the actual saturated swing at the output can go all the way to VDD and all the way to ground. Okay, so the amplitude is VDD by 2. So VDD by 2 root 2, the whole squared, times 1 by RL will give you the power. That is, of course, in this case, if you take VDD to be about 1.8 volts or 2 volts, it will give you something like 8 or 9 milliwatts. Okay. You can increase the power even further by decreasing RL, use an impedance matching network. Okay, so the effective RL seen by the power amplifier is much smaller. Okay, but of course there is a limitation for that also. All of these are all design spaces. You can, changing impedance seen by the PA can be done for any PA configuration, right? This is not something unique to this. Okay, so the point is RL cannot be arbitrarily reduced, because eventually you will hit the limitations of parasitics, okay, parasitic resistances, limitations of quality factor of the matching network components. Okay, so the next thing we did was replace the current source. Okay, remember that an ideal infinite inductor can also behave as a current source. So therefore, we basically took the same circuit but replaced the PMOS transistor with the current source. Okay, the thing that changes is that now the bias current is completely set by the NMOS transistor bias voltage VB. Okay, and the width of the transistor. Okay, you can now set the width and bias current independently. The inductor will just get charged to that bias current. Okay, and then it won't change. Okay, the output bias voltage is VDD. Okay, the output bias voltage is VDD. which means you can now swing much higher. On the upper side, there is no limitation on the swing. I mean, I said there is no limitation yesterday, but of course there has to be a practical limitation, right? What is that? It is a breakdown voltage of the device, M1. Okay, there is an upper limit which is the breakdown voltage of the device. Normally that's larger than VDD, much larger, that's typically larger than 2 VDD. Okay, so it's normally okay. But there are of course reliability concerns, because remember that the device is not expected to operate at anything more than drain voltage of VDD. So there will be reliability concerns, in which case you do something else. Okay, fine. The maximum output power from this circuit now is VDD minus VDSAT is the maximum swing. Okay, that squared by 2RL will give you the maximum output power. In this case, that's about 40 milliwatts. Okay, you can automatically see it's like 1 order of magnitude higher easily. Okay. Then we said you can again use the matching network to reduce the impedance and so on. The next metric that we looked at was efficiency of the PA. Okay, clearly efficiency is can be one metric of efficiency can be easily defined by taking the power delivered to the load, okay, and taking the ratio of that to the power taken from the VDD. That will give you the efficiency. Okay, the point is, I didn't mention it yesterday again due to lack of time, but since we have now come to today's class, we'll also look at the other definition. This is actually called drain efficiency, and normally for power amplifiers there is one more efficiency that we are going to look at today. This is called the drain efficiency. The drain efficiency is now power delivered to the load over power taken from VDD. Power taken from VDD is clearly VDD times I bias. The bias current needs to be set to a certain minimum value. We use the swing limit condition based on the triode limit, VDD minus VDSAT. But now we pointed out that there is also a current limit. Okay, so there needs to be a minimum I bias such that the signal current does not go below 0. Okay, that means that the bias current should be at least equal to the signal current amplitude. How do you get the signal current amplitude? Maximum output power, okay, condition should be equal to IRMS squared times RL. Okay, that will give you the maximum signal current. From that you back calculate the maximum DC value. Does it make sense? Or the minimum bias current that you should give for the circuit. That you get from the cutoff condition, and we looked at all of this. Okay, any questions on this before we move on? We came up with a way to set this, to set the width of the transistor. Finally we kind of ended by saying that the maximum possible efficiency is 50% for this, if you want to operate in a linear fashion. Okay, that's kind of where we ended. Do you have any questions or anything that you want me to cover before we move on? What do you mean that's okay? I don't understand what that means. No, I don't understand. Okay, so let's go to the definition. I don't understand what you mean by proper definition or okay or something. So maybe try to rephrase your question. No questions now suddenly. Okay, so this is the, maybe now that you have brought it up, I'll define the other definition of efficiency. Okay, can you imagine something else that needs to be taken into account for efficiency? Huh? Power is given from the signal source. We have completely ignored that. If I take a black box, the PA as a black box, it has 3 terminals, right? Or 3 sets of terminals. So let us say ground is a reference terminal for both RF and DC. You have VDD, you have input, and you have output, correct? So right now we have only considered these 2 terminals. Okay, but remember that there is a terminal here. Okay, and power can be given in from this terminal, okay, in certain cases. Okay, now it turns out for CMOS power amplifiers, this may be less of a concern, but not always. Okay, let us look at this. What is the input power? If you just look at the PA that we have seen so far, what is the power given to the input of the PA? 0, right? The input is capacitive. Are you giving any real power to the input? Of course not, right? You are only giving in reactive power, correct? So if the input impedance is capacitive, okay, you only give in reactive power, you do not give any real power, resistive power, okay. Therefore, your definition of drain efficiency is correct. I'll call it DE, okay, is the total efficiency. But if your input has a real component, and this is possible if you go to, for example, even for a CMOS PA, if you go to high enough frequencies, there will be a gate resistance. What really matters is how on the relative values of the gate resistance and the gate source capacitance. Remember, if Zn becomes so Zn, I'll put it like this, I'll write it like this. Remember, how do you draw? All of you know, I think by now, the transistor from the gate, it has a okay, polysilicon gate, okay. Depending on the width of the transistor, you can draw the dimensions of the transistor. So let us say I have, let us say, 2 or 3 fingers, I don't know, you can have many fingers actually. I'll show the case with 2 fingers, okay. What I'm going to do, I put on a metal, this is my gate terminal, this is polysilicon, okay. Now the channel, where is the channel? The channel is under the gate, correct. So one side is the drain, other side is the source. So let us say drain, source, drain, okay. And I'm going to connect the 2 drains using a metal layer. This is a 2-finger transistor. All of you are aware of this structure, layout of the transistor, okay. Now the point is, the going from the gate, right, to the actual channel. So of course the channel is right under the gate all the way across the width of the transistor, correct. So this polysilicon actually has some resistance, okay. This polysilicon actually has some resistance, okay. Of course it will, it is not 100% conductive, okay. It does have some resistivity, normally that is lower than the metal resistivity, okay. So the effective model of the transistor that you have to draw should include a gate poly resistance. So the problem is that this is a distributed resistance, it is not a fixed resistance, because you can think of the transistor as you can slice this gate along the width of the transistor using infinitesimal sections, okay. You have a whole bunch of these transistors, okay, in parallel, okay. Each one of them has a different gate resistance. You can come up with the actual effective gate resistance for a given width, okay. You can reduce this in many ways. So for example, you could have chosen to connect these on metal. Metal is much less resistive than poly. I could do a dual gate connection. I'll connect the gates signal from both sides, in which case I would just cut the poly resistance by about half, correct. Okay, what else can I do? I can reduce the width of the each finger. I now increase, if I double the number of fingers from 2 to 4, I'll reduce the poly resistance again. Obviously you cannot do this indefinitely, correct. You cannot keep doing this indefinitely because there are overheads to layout, so those parasitics will also start mattering, okay, both capacitive and resistive. So in the end you are going to have some effective Rg in series with the CGS of the transistor. Does it make sense? Now, if I go to high enough frequencies, right, you can see that Rg can become a significant proportion of Zn, right? 1 over omega j omega Cgs keeps dropping. The reactive component keeps reducing as a function of frequency, right? So Rg will become more and more dominant at higher and higher frequencies. Okay, it so happens that for the devices that we're talking about in the gigahertz range, the gate poly resistance is less prominent than it, such that for hand calculations you don't need to take that into account. But if you go to high enough frequencies, you can see that it will matter, which means you do give in real power. How much real power do you give in? What plus k square? IRMS going into the times IRMS squared going into the gate. Okay, how will you find that out?
We can find the current. If we apply input the voltage, V by R plus 1 by Z omega CTS.
Okay.
So V into I bar complementary function. The real part of that will
give you the real power. Okay. Now I am going to work it out in a different way, because Vin is really not a direct spec for the PA. What are the direct specs for the PA? Remember, I am interested in efficiency at maximum output power. Correct? That's what we have been calculating. That is where the efficiency is. I am having maximum power delivered to the load. I am setting everything based on that. I need that much I bias. Right? If I back off from that, efficiency will get worse anyways. I am setting it, designing the system such that I get 50% efficiency at P out max. Okay. Now, the input swing for the PA is clearly P out max over the gain squared. Correct? At max power, okay, so you can V in, okay, is V in max, or rather P in max, okay, is P out max over the power gain. Okay, but because we are talking about a CMOS PA, we don't know what the power gain is. Okay, so therefore I am going to start off with V in max. Okay, in a general PA, if you already know the power gain and the output power, you can calculate the input power. Okay, for a CMOS PA, I don't know, okay, what the power gain is, because I have so far been assuming that the power gain is infinite for the CMOS PA. So I'll start off with V out max, which I already know as a part of design, over the gain. Does it make sense? Where gain is just the AC gain while driving RL. Now, based on this V in, I can calculate P in. So the input current is V in max by mod Zn, correct? So squared times 1 over 2R. Of course, the 2 comes from 1 over root 2 of the amplitude. Okay, I'm just like rest of circuits, I'm assuming everything is in terms of amplitude, V in, V out, etc. Okay, this comes from the RMS value. Oh, sorry, times Rg, sorry, not RL. Okay. Is the input current. Oh, sorry, of course, sorry, I am not doing the voltage, right? Sorry, thank you. Into just Rg. Okay, into Rg by 2, that's right. It's I square R. Okay, this is the input power going in. Okay, and as you can see, it depends on the gain, it depends on Rg and Zn. Okay, Now for a CMOS PA, this is normally quite low at low enough frequencies. But if you go to high enough frequencies, this can become significant. So in fact, because of that, I am going to define a new metric of efficiency, which is called the power added efficiency. Okay. What is the power added efficiency? Anybody knows? PAE? How will you define it? Output power by input power plus PDC, right? As you can see, okay, if the gain is very large, this PN will be very small, right? If the gain is large, PN can be very small, and therefore the PAE can approach the drain efficiency clearly. Okay, so for a high gain circuit, PAE and DE will be almost the same, and normally both of these are represented in terms of percentage. So maybe I'll also, I don't know if I put in the percentage there explicitly, into 100. Okay, normally it's normal to express efficiency in terms of percentage. Okay, any question? Okay, now if you are not designing a CMOS PA, if you are designing some other PA, okay, of course the CMOS transistor, you are lucky it has a high input impedance, but that's not necessarily true for other types of transistors. Okay, in which case Pin does really matter. Okay, if the input is not resistive, Pin really does matter. Okay, it's not just that. If you are building a CMOS PA, you are going to integrate it with the rest of the transmitter, right? So the output of the transmitter is also CMOS. It can drive this capacitive input, no problem, right? But imagine that the PA is a separate module. You are building a standalone power amplifier module, which is the way you will get it. If you go outside and ask for a power amplifier module, you can get it. Okay, that can be built from any technology, right? All you know is the datasheet specs, right? Now that PA has to be matched at the input and output, has to be matched to 50 ohms at the input and output. Okay, there is no way around it, because the way it is going to happen, that PA is going to be packaged. Okay, you are going to place it on a PCB, you are going to route from rest of the transmitter to that PA, and then from that PA to the antenna. You don't know that length of line, right, can be several, you know, a significant fraction of the wavelength. Okay, has to be matched to 50 ohms. The transmission line has to be 50 ohms. So a PA module okay, this has to be done. If you build the PA, CMOS PA as an integrated module, you don't need to match the input, but very often you need to match the output. Okay, let's quickly see for this case. And by the way, the minute you match the input and output to 50 ohms, PAE does matter. I hope you see that. Input power is always, there is always, it is not just RG is very small, etc., etc. The minute you match the input, has a real component of 50 ohms. You are delivering power. Then it just depends only on the gain, on the power gain of the module, S21. Does that make sense? If S21 is very large for the PA, then again PAE will approach drain efficiency. Okay, fine. Now let me see, let us take this PA. How will you match this PA to, let us take our I want to match at input and output to 50 ohms. Let's say in this case I am not using any, I am taking the simplest possible structure, right? I want to match at input and output to, So Vs and Rs, a Thevenin equivalent of Vs and Rs is driving the circuit. Okay, I want to match the input and output of this PA. How will I do it? Let's look at the input. How do you match the input? Small signal analysis. Why? What is the input impedance of the MOSFET? Rg plus 1 over j omega Cs. How large is Rg going to be? I told you that even at a few gigahertz, Rg will be very small. It will probably be a few ohms. Correct? So it's not going to give you 50 ohm matching. How will you do this? Huh? Source degenerated. So he's suggesting source degenerated. So let us see if that will work for us. So he's suggesting an LS that will give you, it will give you a real part of 50 ohms. Okay, you can do it like an LNA. You put an LS, source degeneration, this is omega t times LS, and then now you will know what will you do? You will add an LG, right? You could do this. Okay, that is possible. What is the downside of doing this? There is a very significant downside if you try to do this. Of course, it will give you input matching. The PA is very big, so you don't get what? Sure, but that is less of a concern to us. That is true. So the PA is he's suggesting that the PA is very large. So anyway, CGS is going to be very large. So the Q input matching Q is going to be very small. That's okay. Because this is after all incidental, right? I didn't plan to have this thing. If the Q is less than 1, you'll have to make that up in the gain of the PA. That we know. Okay, that's one thing. Signal current has? Well, of course, the signal current will actually flow through LS. So what will be the voltage developed here? Now what will happen? The signal current will now develop, if this is the sinusoidal signal current, you will now get a sinusoidal signal voltage here. Correct? Of course, you have to across LS. That current has to flow through LS. Now what will happen? This is now going to affect your output swing. Earlier you assumed that the source of the transistor was a ground, output can go down all the way till VD sat. Correct? Okay. So does it get worse or get better? I think that's the question you need to ask yourself. Does the swing limit get worse or does it get better? So when the current waveform is like this, what does the output waveform look like? You have an inversion. Correct? You are drawing current from this thing. So the output voltage will look like this. Okay. As you can see, when the drain voltage is going low, the source voltage is going high. Right? Of course, because from gate to drain you have an inversion, gate to source you have the same swing. Correct? This is clearly a problem, isn't it? You can't have this. Earlier you had 0 and you had this low swing. You set this to VD sat. Now, depending on the value of LS, you have just lost this much swing. Okay? You have reduced V out, you have reduced P out. Clearly a bad idea. Okay? Okay? So what else would you do? What is the number one thing most important? Of course, P out is the number one most important thing for the PA. Number two most important thing is the efficiency. Number three most important thing is the gain, and so on. You can prioritize this in some good fashion, right? Does noise ever come into the picture for the PA? Normally no, because the signal that you are putting out of the DAC is already several hundreds of millivolts. You are gaining that up further. The signal going out through the antenna is several volts. Okay, so noise is not a concern at all. So really, for a CMOS PA, one of the easiest things to do is simply to put a resistance, a 50 ohm resistance at the input to match. That is a very straightforward way of matching if you need to build a discrete power amplifier. But normally, you don't build a discrete power amplifier with CMOS because already CMOS, does not give you as much output power as you want, right? It only gives you tens of milliwatts. I told you cellular requires watts, right? There is just no way of getting out watts of power from a CMOS PA very reliably. Okay, a lot of people have tried and failed. Okay, so it doesn't make sense to do all of this, right? Why add 2 more inductors, do all of this? It is just a lot easier to do something like this. Now what I'll do is for now I'll just say that I'll do something like this. Okay, but you may not always choose to do this, but the way I'll show it is RB is equal to RS. But normally you don't want to do this. The reason is you don't know that the impedance here is 0. Okay, so explicitly this is not a good idea. Okay, so what you would normally do is maybe put in a 50 ohm resistance to ground on the left side of the left side of the decoupling capacitor. Okay, does it make sense? Yes, that is correct. You get half the gain. It's not half the power. You just cut the gain in half. Correct? But that is always true. Whenever you match at the input, the available power goes down. You know this. Whenever you need to do a matching, see, the thing flows the other way. You have a distributed system. You know the dimensions of your signal transfer reach the equivalent to significant fraction of the wavelength. You automatically can only get a certain amount of available power, right? In this case, that takes the effect of getting half the signal voltage across the gate source. Therefore, you need to make up that gain. Okay, things are going to get worse. Okay, just wait and see.
Why can't we use RS? But
yes, you can. So what he is suggesting is match from Vs to Rg, right? You could do that, but the problem is if Rg is extremely small, okay, you will need a really high Q matching network. Imagine going down from 50 ohms to 1 ohm or half an ohm. Okay, you will need a really high Q matching network, okay, which is extremely difficult because now the quality factor of the components are limited. Imagine the quality factor needs to be 10, okay, but the inductor quality factor is already 10. What will you do? How will you build a matching network with that quality factor? Extremely difficult. Okay, the limitation comes from technology. Theoretically, it's possible.
I was suggesting something. So, at the output of the gates, we have the source impedance RS, and we are using RS to terminate it.
Yes.
Why not use that RS to be a high impedance and match between that and that so that you get higher swing input?
You can do this, but can input power ever see the matching network is a lossless network, right? Can the input power ever change? Power doesn't change. Swing changes. So in other words, what you're talking about is, so this is exactly equivalent to putting a transformer at the input. By the way, a matching network is almost the same as a transformer. So all you're saying is get some passive gain. Of course, that is definitely. I could even put a transformer here, by the way. I could just simply put a transformer, well, before this, right? I could simply put a transformer here, right? Instead of putting it to the left side, I could always do that. Getting passive gain is not a problem. Okay. Getting the, getting power gain is a problem. Getting active gain is not a problem at all. I mean, getting passive gain is not a problem at all. Okay. You can put an impedance matching network, transformer, etc. to get passive voltage gain. No problem. That you can do for any circuit, by the way. For any circuit, you could just say, I want to increase gain, therefore put a transformer with certain turns ratio. Correct? You could always do that. So this is like saying, I want to increase Vs. Let's say the mixer is driving this, I'll just put a transformer at the output of the mixer. You can put a transformer anywhere. Okay. Any other options? So you just lose voltage gain. Okay. Okay. Now what about matching at the output? How do you do matching at the output? So if you do this, or is very good. With caveats, by the way. The reason is, at low frequencies it will be very good. At high frequencies you now have the capacitance. Correct? Of the device. How will you get rid of that? You will now also need an inductor to tune out. You can get a narrowband PA by using an inductor to tune out the input capacitance of the transistor. Okay. I'll just show that conceptually like this. I'll call it some LB. Okay. So if LB has a finite quality factor, you now need to change RS prime okay, such that the overall input is 50 ohms. Understood? So the understanding is that if its inductor is not ideal, input impedance will change. Okay, so the input impedance after RS prime may actually be 500 ohms. In which case you can't do 50 ohms, maybe 55 ohms or something you will need. Okay. So that this is what you would choose. LB is chosen such that it resonates CGS. Now you now have a narrow band input match. Okay, for a CMOS PA, this is specific to the CMOS PA. Okay, if the input matching, if the input impedance was, let us say, 10 ohms, right? Let's say you are using a gallium arsenide device, gallium nitride device, bipolar device. Let's say input impedance was smaller. You might just choose to put an input matching network, and in fact that will be the more general case. I am teaching only the specific case of CMOS PAs. Okay, in general you will need an input matching network. I'll call it an input matching network. Now you also need an output matching network somewhere here. Okay, what is that output matching network that you will need? Sure. Okay, so now we are getting to the specifics. Okay, I need to resonate out CDP. So instead of an infinite inductor, I'll just call this LD. Okay, now I'm building a truly narrow band PA. Okay, so now we can, RL prime is chosen. So choose RL prime so that S22 is low. Make sense? Any questions? Now, yes. Good question. He's asking what happens if you don't match the output. Okay, people do that sometimes, occasionally. So I'll draw the signal picture of the transistor. So remember that the transistor has some RDS, by the way. So RL prime is chosen so that S22 is 0. The inductor might have a finite Q. Okay, the output impedance of the transistor might be lower and so on. You choose RL prime not necessarily at 50 ohms, but the values which will give you 50 ohms effective impedance at the output port. Okay, now let us say I don't put RL. Okay, what is going to happen? Of course I'm still going to put a 50 ohm transmission line, right? And this is 50 ohms. This is GM times VGS. What is going to happen? So of course I put in a signal at the gate, correct? The current coming out is going to be in phase with that signal, GM times that signal. It is going to try to split, of course, between RDS and 50 ohms. What is going to happen? That's right. So if RDS were not there, actually consider the case, let's consider the more ideal case. Let's assume that RDS is not there, right? Yes, of course the device is not matched. All of this current is going to flow out. Okay, the point is, because it's not matched, if you have any reflections, what is going to happen to them? Clearly you will have a standing wave, right? Depending on the mismatch, you will have a standing wave there. You can develop very large voltages. right? If you have an ideal transistor, no problem, ideal current source. The minute there are two issues you have to worry about. The minute you have an RDS, that will now produce signal current. Signal current is no longer just simply Gm times VGS. Coming out of the transistor port is actually Gm times VGS plus VD by RDS. That VD is not just the instantaneous drain voltage which you did, but there are also reflections happening. If you have an ideal matching at this end, it will look like nothing, everything is fine. Correct? But there are other cases you have to worry about. This is anyway connected to the antenna, right? The antenna might receive some junk while you are transmitting. What is going to happen to that junk? That junk is going to come in, right? Now that junk is going to get multiplied by the standing wave ratio to give you a large drain voltage. So the point is, you do this to prevent the PA from getting disturbed. You do output matching to make sure that the PA conditions are well defined. Okay, so if you match the circuit, all these things will be damped. Does it make sense? So in general, because you are now designing the circuit to operate at the absolute maximum voltage possible at the edge of breakdown, etc., any additional swings you do not want to tolerate at the drain of the device. Okay? Any other questions? Now, if you are just going to build this to test it, you may not bother with matching at the output, for example. You will still need to match at the input, because imagine now you are testing the circuit, you build the PA. You are going to use a network analyzer to test it. You don't have an antenna there. The network analyzer has very good 50 ohms. The cables are going to have very good 50 ohms, right? They are all measurement equipment which have very good high grade cables, high grade equipment. Okay, you will not see any random reflections from the other end. Okay, so normally it's a well defined scenario environment where the PA is working. You can choose not to match the output. S22 will be bad, so what? Nothing. Okay, there is no additional signal coming in from the VNA. Okay, the input still needs to be matched because you want to know exactly how much S21 the device is able to sustain. Correct? So therefore you want to know predictably what the gate source voltage of the device is. So input matching in general is a must when you are testing a standalone CMOS PA. Output matching sometimes you can get away with, but if you are really using it in a real system, you will need to do output matching. Okay? Remember that. Okay, let us come back to output matching. How do you do output matching for the PA? So now,
What sort of signal that comes that is absorbed by the antenna from outside?
it could be other signals, wireless signals. It could be your own transmit signal getting reflected back from a very nearby interferer. So imagine you put out a wireless router in the corner of the hall, in the corner of the roof, right? You basically have three reflective surfaces right next to it. What do you think is going to happen? The antenna is going to try to put out stuff. It's going to hit the wall and come back, right? It's a significant amount of power. What is going to happen to that? It's going to travel along your transmission line, go to the input or output of the PA. If it is not matched, it will again get reflected back, get radiated. It will cause a whole amount of issues, both for the PA as well as for the transmitted signal. Okay? Yeah. Receive antenna will normally receive a whole bunch of things. It will receive the direct signal, it will receive signals reflected by a whole bunch of reflectors. You just cannot predict. Okay? What you can do is you can predict the approximate behavior, right? That you can do. Because remember, if you had an omnidirectional antenna, for example, you are radiating out into a solid sphere. So typically it will go as 1 over r squared, the power. But the actual power which you receive at the receiver will not go as 1 over r squared. Okay, it may be much lower because of reflective paths. Okay, because of fading. It's called fading. Okay. If you get a null, there's not much you can do except for move to a different point. Or design an alternate second receiver which is some exactly lambda by 2 away. You could do that. Okay. Yes. Yeah. Yeah, we're going to come for that. We have not discussed the output matching network yet, right? Did I? I discussed the most basic one, right? Correct. So I guess your question is now valid, right? Why not use an output matching network? So let's draw this. So this is the circuit that we have seen. Okay, this is RL prime. Okay, now he is asking, why not put an output matching network? Let us say you do this. The output matching, irrespective of whether you have a, first of all, if you, instead of 50 ohms, if you had matched that down to 10 ohms, you will need an RL prime that corresponds to 10 ohms output impedance. First of all, this RL represents whatever is matched down from 50 ohms if necessary. First of all, okay. Now what he is suggesting is, right, why do matching like this, right? Why not match down to the real part? Is that what you are asking? Okay, so let me draw that in a slightly different way. I'll draw that in a slightly different way to make it more specific to our case. Maybe I'll just repurpose this. So he's saying, I take my circuit, okay, I measure R out, okay, whatever it is, I measure R out, and what I'm going to do, I'm going to okay, an output matching network that brings RL to R out. Definitely possible. Okay, but there is a big problem with this. The question is, what is that problem? Huh? High Q, not necessarily. Well, it is high Q, it so happens, but there is an even bigger problem. Power always splits between your own resistance. The minute you match, right, power always splits halfway between your resistance and the load resistance. Remember that. You can use ideal components. You let us assume that you use ideal components, you are allowed to use ideal components of any value. There is a much bigger problem unrelated to the output matching network itself. Exactly. The problem is that R out is much larger than RL. What is the R out of your circuit as you have designed it? It is literally infinite. You put an infinite inductor, RDS is infinite, very large. So the way you have designed it, the output impedance of a circuit is extremely large. RDS, even for these large transistors, may be a few tens of ohms, okay, but as you will see, you will need a cascode for this circuit. The minute you put the cascode, the output impedance will necessarily go into hundreds of ohms. Okay, so normally the R out of your circuit will be much larger than RL. What is the problem with that? Problem is P out. Exactly. So remember that P out max, what is P out max? Was approximately VDD squared by, what is the maximum swing? You could get VDD swing from this, ignoring VD sat. Okay, so VDD squared by 2 R out. Okay, this will clearly be much less than VDD squared by 2 RL, because R out is much smaller than RL. Okay, remember what we want to do, we want a much smaller RL, not a much larger RL. If you try to match to R out, you will not be able to get enough power out of this system. Even though the circuit can swing higher, right, you will not be able to do it. Right, for that same amount of swing, you will not be able to get enough power, that's what I mean. Right, the circuit can swing VDD, right, but if R out is getting larger and larger, you are stuck with getting smaller and smaller output. Okay, so this in general is a bad idea. For CMOS PAs, now there are other PAs where it's possible. It all depends on the output impedance. If the output impedance is low, then you can do this actually, no problem. Okay, and there are indeed a lot of PAs where you can do this. Or the output swing is not limited by VDD. Okay, you can do this. Okay, yes. Quality factor of LD.
Choose LD with a small quality and such that you will get impedance close to.
So you could explicitly choose LD with a small quality factor. So he's suggesting doing that such that the output impedance is what, 50 ohms, right? There is a small problem with that, and I'll tell you what the problem is. The PA is normally going to take several tens of milliamps. Okay, normally to make sure that you don't burn up the wires that make up the inductor. The inductor is basically going to be a spiral metal layer. Create a spiral inductor using a metal layer. You folks have seen this. Now the current to get a, let us say this thick circuit is going to take a few tens of milliamps. Okay, you're going to put out 40 milliwatts with to a 1.2 volt power supply. How much current do you think a 1 volt power supply? How you probably going to put out about require an I bias about 40 milliamps, signal current of about 40 milliamps. To support an I bias of 40 milliamps, you will need several tens of microns of width. Okay, choosing LD low Q is difficult if your width of the trace keeps getting larger and larger to meet the current density requirement. Okay, it is just much more straightforward to explicitly put a resistor in parallel to ground or VDD. You could put a resistor to VDD like this if you want. That may look like dequeuing the inductor. I just showed it on the right side as a resistor to ground. That's all. Okay. There is a second problem with dequeuing the inductor. Remember that the inductor was supposed to be ideal. So the output drain bias voltage was supposed to be VDD. In reality, the inductor is going to have a DC resistance. If you tinker with the DC resistance, you are going to get a significant voltage drop here. You do not want this. You want this to be very small. If you try to dequeue the inductor to get the 50 ohms from that inductor, you are now going to start increasing delta VDC. It's going to affect everything, maximum swing, etc. Okay, you don't want to do this at all. Don't touch the inductor. Okay, the inductor you wanted it to be infinite with infinite Q. Then you made it LD to resonate out CDB. Okay, don't tinker with that. If you try to do too many things with the same component, you might head into trouble. Okay. Any other questions? So this is a problem. So getting P out is a problem. So for the CMOS PA, it's much straightforward. If you need to do output matching, much more straightforward to just put a resistance to signal ground. Okay.
So to support high current, inductor has to be required. So SRF is not
SRF
done.
could be a problem, right? In which case you would make the inductance smaller. Okay, for a higher SRF, put some explicit capacitance. All those things I will not kind of explicitly touch, but you could always choose an LD and put an explicit CD across it, so that the total capacitance is CD plus CDB. Okay, then the effective inductance will start reducing. Okay, then the SRF will automatically keep increasing. That's all. Very simple. It's fairly straightforward to do that. Okay. Any other questions? Okay, so now I think you guys know how to design a linear CMOS PA, right? If you need to do input matching, output matching circuit, do you know how to do it now? It's very straightforward, right? Can you calculate the gain? Of course, you have a gain of half at both input and output, right? Because of matching. Then what you will get is actually GM R out or GM R. Well, if you don't have a matching network, GM RL by 4 is what you will get. Okay, the overall gain of this. Okay, voltage gain. Okay, so now good thing I wanted to discuss that, I almost forgot. So now the requirement for the cascode, suppose you stop here. Okay, now the problem with this circuit is that, so let me again LD maybe this time I'll just show it like this. Okay, or RD. Okay, to match. This is my biasing circuit so far. I mean my input match, output match PA so far. Yes? Yeah. So what? You can put it to VDD on this side. Well, I called it RD because I connected it to the drain. If I put it this side, I'll probably call it RL prime. Doesn't matter. You choose RD or RL prime such that output is matched. Does it? So the same RL prime, if you connect it to the left side of the infinite capacitor, it has to go to VDD clearly. You don't want any DC current, right? You don't want to change the bias point. Correct. That's what I just showed as RD on the left side of the capacitor. No, why? VDD is an AC ground, no? Why will the AC get affected? VDD squared by? Correct. What is the maximum swing available at this node? What is VO max? VDD. Correct. What is the maximum power delivered to RL? RL. The voltage across RL is, maximum voltage across RL is VDD, right? So VDD squared by 2RL will still be delivered to the load. There is no change in the maximum power delivered to the load in this case. What will change is the gain of the circuit. The efficiency of the circuit has just been cut down. I hope you understand that. To deliver the same amount of power, I am now burning half the power in RL prime. So automatically efficiency will come down, ideal efficiency will come down from 50% to 25%. Understand? Not 50% to 25%. I think it will come down from 50 to 33, I think, in this case. Because you are now putting out half the current in the device and half the current in the loads, right? And one half of that is going to RL, right? Okay? Yes, that is going to come next. I have not done that. I have not finished yet. Because I have not started that yet, you can't ask that question. Okay, let me start about why you need the cascode first, then you can ask your question. Okay, fine. So this looks great so far, but there is a problem. Okay, the fundamental problem is that for a CMOS transistor, there is a significant gate drain capacitance, overlap capacitance. It can be significant in this case because the width of the transistor is very large. Okay, since Wn is large, CGD will be large. The minute CGD is large, you now have an inherent feedback path. Okay, so there is a potential now for the PA to become unstable. Okay, especially at higher and higher frequencies, 1 over j omega CJD becomes smaller and smaller. Okay, and of course there is a phase shift, okay, through CGD, clearly potential for instability, right? Correct? Okay. How do you make it stable now? Cascode. The thing is, remember right from the beginning, the cascode helps you get unilateral behavior. In the case of the LNA, the stability would still have been a concern even for the LNA. Okay, we did not have a strong swing limit, so we went ahead and added it anyways. The advantage of the cascode is that automatically whatever you do at the output does not, the cascode transistor, the common gate transistor, okay, is like an ideal current control current source. Whatever you do at the output does not affect you at the input, right? It has an infinite output impedance, very low input impedance. Okay, because of that, you do something at the output, nothing will happen at the input. Okay, same thing here. Okay, if you need to fix this, a cascode is one of the most reliable ways of fixing this instability problem. Okay, so of course, all the other ways you discussed are also, during the LNA case, are also possible. For example, you can try to resonate out this capacitance, okay, using an inductance. But there is a problem. If you try to resonate out this, CGD is large enough to cause instability but too small, okay, to require a small enough inductance. The inductance required may be very large. Okay. Second problem is bias. The inductance causes a DC short. So now you need to add a very large cap in series with the inductance. Area is now blown up. All these issues will be there. Okay, so cascode is much simpler, is a much simpler way to solve, to to solve this problem, but with a downside, which is that the output swing limit gets affected. Okay, so now let us see how to fix that. So, or let us see how to improve the output swing limit at least. So now I'm going to add a cascode. Okay. Have I missed out anything? I have now added a cascode. Okay. The gate of the cascode needs to be connected to VB2, some bias voltage. Now, of course, if I chose VB2 equal to first step is of course do the regular cascode. What do you normally do? VB2 equals VDD, correct? You try to do that. If you do this, what is the maximum output swing? Huh? It will just be VT of the cascode transistor. It's just VT2. Remember, VT2 can be a little bit larger than regular VT because of the this thing effect, because of the backgate effect, right? Just remember that. But it will be a little bit larger. Maybe instead of 500 millivolts, it may be 600 millivolts. Okay, but not appreciable enough. Okay. This is a problem. We have just spent so much effort trying to maximize the output swing. We have just brought it back down to VT, right? This is clearly not tenable, right? You want to set it back to as high as possible. How will you do this? Of course, the obvious thing to do is to start reducing VB, where VB2 does not need to be equal to VDD. If VB2 were equal to, what is this voltage? I'll call that Vx. What is Vx? Is clearly VB2 minus VGS2. Okay. The point is, if you keep reducing VB2, okay, Vx will keep reducing because the current is supposed to be constant through M1 based on VB. For an ideal transistor, that is indeed true. Okay, because RDS we assume to be 0 when we start. But remember, these are thin oxide transistors. These are, the not thin oxide, very short transistors. The length is extremely small. Okay. Therefore, the RDS can be significant. Okay. All that means is that you will have to increase VB, most probably VB1. Okay, it is quite possible that when you do this, you might need to increase VB1 a little bit, not at the same rate. Okay, but you might need to increase VB1 because of the lambda effect. Okay, just remember that. If you ever have to design this in practice, because of the lambda effect, you might have to increase VB1 to keep our ultimate goal. So that is why right from the beginning, I have never been biasing you towards biasing with VB1. I have always said drain current. What you are interested in is a particular I bias. Based on the bias conditions of M1, you apply the appropriate VB1. Just remember that. Because it is at the end of the day the bias current that actually sets the cutoff condition. Okay? Any questions? Okay. Now, I start reducing VB2, right? Vx will of course reduce at almost the same rate, because if I bias is constant, if I increase VB1 to keep I bias constant, VGS2 has to be constant, correct? VGS2 has to be constant, except there is again a second caveat to that. Okay, VGS2 may change slightly because M2 will also be, it's going to be identical. Normally you would just choose M2 to be identical to M1. That will also have a very small length. And remember that this VDS is increasing. Okay, so that might change VGS slightly. Just remember all of these second order effects. These will all be significant in the PA because the transistors are going to be extremely wide, okay, and minimum length. When I say extremely wide, don't be surprised if you want to put out max power, don't be surprised if you have transistors of the in running into millimeters. 1 millimeter, 1.5 millimeters for the NMOS transistor is definitely possible. Okay, don't be surprised. You want to put out 40 milliwatts of power, this is what you have to put out. I know you're used to like 10 microns, 20 microns, this kind of stuff will happen. The minute you do this, okay, you make it this, you can imagine the amounts of capacitance. You are dealing with picofarads of capacitance everywhere. Now you see why CGD is a problem. CGD is probably going to be like 200, 300 femtofarads, half a picofarad. These kind of CGDs you would never have dealt with. Okay, it can easily become unstable. Okay, and with these kinds of things you will see all kinds of second order effects. For example, you will suddenly see that for such a wide transistor, threshold voltage is changing as a function of the width of the transistor. It is possible. It was supposed to be 400, it's suddenly something different. Those kind of second order effects you should plan for, you should expect. Okay, now I do all of this. I have now reset it to a new point. What is the minimum value of VB2 that I can set it to? VB2 min is equal to VDS2. Vx is VDS2. Okay, don't tell me VB2 min is VDS2. Vx is reducing. What is the minimum value of VB2?
Plus 3 over
Vt plus 2 overdrive. Okay, it is basically VGS2 plus VDSat1. Okay, that is the minimum voltage that you can set VB2 to. Okay, VB2 min will happen at Vx min. Vx min is clearly VDSat of M1. Okay, that is purely from a bias condition. In reality, remember if you choose M1 and M2 to be identical, Vx will also have a swing, which will be equal to the negative. You will get a gain of about 1 from this node to this node. Okay, so if the gain of the PA is not very large, okay, this can be significant because VDSat is about 100 millivolts, 150 millivolts. Okay, for an output swing of let's say 1 volt, if the gain of the PA is about 10, you can easily have a 100 millivolt swing at the input. Okay, so apart from the DC bias, you are now going to have a swing. So let's assume that this swing is like this. You are now going to have a negative swing. It is out of phase with the input. Okay, so clearly you are actually moving it closer to triode. So for the bias, you will need to give, I will write it in this manner, VDSat1, okay, plus the maximum swing, the amplitude of the swing you will get, okay, plus, I'll just write it as VGS2. Okay, does it make sense to everybody? VGS2 plus the swing you expect plus VDSat1. The condition is going to be that M1 should never enter triode. Any questions? So you should bias it such that it just touches the edge of threshold. Yes. So, okay, so why should it be 2 Vx max? So at this point it is just VDSat1. Correct? At the lower end, so this is Vx max. Correct? We are going to design it such that at the lower end, at the lowest possible swing, you are going to be at just at VDSat1. At that point, so you basically add VDSat1 plus Vx max gives you this bias voltage. That plus VGS2 will give VB. It can swing above that, no problem. Okay, if it swings above that, it will cause M2 to go into triode. We have not touched that condition yet. Okay, we have only touched M1 condition. So VB2 minimum has to be this. Now this can clearly be much less than VDSat. Okay, because if your PA has enough amount of gain, let us say Vx max is 100 millivolts, VDSat1 is another 100 millivolts. You are clearly saying that it should be 200 millivolts plus VGS2. VGS2 may be 700, 800 millivolts. Okay, so it has to be, instead of 1.8 volts, it may be like more like 1 volt. Okay. Lower swing, of course, it is best to have no swing at all, but that's not possible. How will you make Vx not swing at all? You will make the cascode so many times as large as M1, correct? Right? The minute you do that, you are now increasing the CdB at the output. Now the output capacitance is CdB of M2. Okay, you can't arbitrarily increase the cascode size. Okay, and second thing is, remember that the M1 is already like, 1 millimeter. You are now talking about making the cascode like, 3-4 millimeters. This is not going to be tenable eventually, purely because of area and capacitance concerns. Okay. Any other questions? Okay, so now the output swing. What is the maximum output swing? So if you look at the output is now going to swing from here. It is biased at VDD. Okay, what is the minimum voltage at the output? It should be such that M2 does not go into triode, correct? What is that condition? So this minimum voltage is VB2 minus VT2. Earlier it was VD2 minus VD2 because you blindly connected to VDD. Now it is VB2 minus VT2. Okay. So exactly. So it's VDSat1 plus VDSat2 plus Vx max minus VT2. No, plus Vx max. That's all it is. Okay. So this is basically is that okay? VDD minus this will give you the amplitude. It is not as bad as you thought. Let us say gain was very large. Gain was like 20 dB, 20, right? So for 2 volts, you are looking at about what? So for 1 volt swing at the output, you are looking at about 50 millivolts, right? 50 millivolts, VDSat is 100 millivolts, let us say. So you are talking about 150 plus 100, 250 millivolts. So let us say you had a 1.8 volt supply. That's what we worked with yesterday. So instead of 1.8 volt swing, earlier you had 1.8 minus 100, right? Now you have 1.8 minus 300, minus 250, right? 1.55. That's not too bad. Okay, that's not too bad. This is the best you can do while still having the PA to be stable. Okay. And with this, you are now done with the hand design of the PA. Now you should know everything. If I give you a spec, right? In the final exam, let us say I ask you to design a PA, will you be able to do it? I give the spec saying, tell you the transistor has this beta, mu and Cox, right? Design the width and VT is so much. Design this to get maximum swing. This is the power supply. Will you be able to do it? Match 250 ohms at input and output. I think you should be able to. This is very straightforward. You're just using the transistor equations and that's it. Okay? Fine. Couple of more things, right? Obviously, if you're doing a non-CMOS PA, right, everything is changed. Okay? First of all, the maximum swing. So, of course, the first question you should ask is, why not increase VDD? Right? That's obvious. You have tried changing RL, but there are limits. Increasing VDD also has technological limits. Okay, because you break down the device much faster. Now, one of the things is that if you need watts of power, you can clearly not do it with this, because the CMOS device breaks down at a couple of 2-3 volts, 4 volts. Okay, at the drain. Okay, so the drain VDD is supposed to be like 1.5 volts, 2 volts, and so on. But if you take, let us say, a gallium arsenide device, okay, you might be able to operate with much higher voltages. If you take the most popular technology in recent times is what is called gallium nitride, okay, that can tolerate tens of volts. So gallium nitride PAs have a power supply of 28 volts because breakdown voltage is like 60 volts, 55-60 volts. So you can swing from 28 all the way up to 56 and down to 0. You understand? And the additional advantage of those guys, those types of transistors, is that the overlap gate drain capacitance is much lower because the effective mu n of those devices is much larger than CMOS. Okay, if you take a gallium arsenide device, okay, you may be building a, do all of you know what a HBT is? HBT, heterojunction bipolar transistor. Have you heard of this? Okay, have you heard of HEMT, high electron mobility transistor? These are all different types. They are not MOSFETs, they are not bipolars. They're like kind of not the regular bipolar and MOSFET. Okay, they are different kinds of devices with some similarities with MOSFETs and bipolars. They are called HBTs and HEMTs, HEMTs. Okay, now both gallium arsenide and gallium nitride devices have, their devices are built such that they have much higher electron mobilities, for example. Okay, what is the electron mobility of an NMOS in the technology you guys are using? 240, 300. Those are the kind of mobilities you would have seen, centimeter squared volt per second, right? If you take an HBT, it will be in thousands, 5,000, 6,000, 7,000, 8,000. That's the kind of mobility you can get. Automatically, right, the gains of the PAs that you will see will be that much higher. You will see gains of 25 dB, 30 dB and so on. With CMOS, you are looking at more like much smaller, 15 dB, something like that, 10 dB. No, the channel lengths are not available. They will not have 65 nanometers or 100 nanometers and so on. Gallium arsenide, I think you probably get like 120 nanometers now. Gallium nitride you can get about, I think, maybe 120, maybe 0.2, 0.25. Right? The technologies are lagging behind because you are not building like, you are building only PAs with them. You understand, right? So if you get enough power at the frequency that you are operating with, you are good to go. Okay. Similarly, HEMTs will have maybe 1,000, 1,500 type of mobilities. Now the secondary effect of that is that you need, the transistors will be smaller, CGD will be smaller, therefore you don't need a cascode transistor. You can extract out even much higher output power and potentially make the device stable. These things also have input matching and output matching networks because now they can have much higher voltages, right? Okay, so now you basically have matching networks to basically get as much power as possible. The input impedance maybe few tens of ohms, so you can match to 50 ohms directly and so on and so forth. You get the idea, right? Okay? No, it can't. That's not possible today. It will be two separate modules, two separate chips. That's all. If you have a gallium nitride PA or a gallium arsenide PA to drive watt level power for a cellular system, the CMOS PA will act as a pre-driver, as a driver amplifier for that. Okay, so let us say, so the way this will work, I need to put out 1 watt of power, 30 dBm, okay, at the antenna. Okay, so the gallium arsenide PA will need to put out 30 dBm at 2 gigahertz. Okay, that will have a gain of, let us say, 25 dB. Which means the output of your CMOS chip has to be plus 5 dBm. That's pretty much what you're getting at this. What is plus 5 dBm? It's about 4 milliwatts. Plus 4 is about 4 milliwatts. Plus 5 is about what? 6 or 7 milliwatts, something like that. Yeah, that's pretty much what you're able to get out of CMOS at these power supplies, right? It's clear that you can't easily get out, several tens of milliwatts of power or hundreds of milliwatts of power easily. Now it is possible to get hundreds of milliwatts if you match down to a few ohms of impedance and so on. If you really need to cut down costs, you would do it because the cost of gallium nitride, gallium arsenide is much higher at the end of the day. Okay, a lot of wireless LAN chips today do have integrated CMOS PAs because the spec, I think wireless LAN puts out about like few hundred milliwatts of power. So it is just barely possible using CMOS. Okay, Bluetooth definitely you don't need an external PA at all. Low range, short range devices. Okay. Now, I'm going to spend quickly 5 minutes on this. Okay, but it really deserves a much broader treatment. Okay, you're looking at about 3-4 classes more, but there's just no time. Okay. What we have discovered broadly comes under a class of what are called linear PAs. or also called class A PAs. Okay, and really, majority of the reason I call it linear is because you have information both in the amplitude and phase of the signal, correct? So what will happen, your PA has to operate in the linear region. We discussed yesterday, if the PA, there's no information in the amplitude, you're only worried about the zero crossings, all you need is a switch, right? You don't need to do all of this business of trying to bias it in the linear region and so on. The best possible, if your information is carried only in the phase, all you need is a switch, okay, to act as your PA. Okay, in fact a MOSFET built as a switch can be a switching power amplifier. In fact any device, if you configure it as a switch, it can be a switching power amplifier. Okay, and there are intermediate stages which will give you less linearity, closer to switching. So the way this is class A, okay, you define it in terms of amount of the angle of conduction of the device. Angle of conduction means the current flows through the device for how much portion of the clock cycle, of the input periodic cycle. Okay, so in the case of class A, you describe it as having 360-degree conduction angle. The device never stops conducting throughout the cycle. Understand? Now, suppose I decide to get more efficiency. My fundamental problem is the efficiency. If I decide to get more efficiency by reducing I bias, the only way to do it is reduce I bias. Correct? I can't reduce VDD. I have to reduce I bias. I'll start clipping, correct? If you start clipping, you will automatically become nonlinear. Fundamentally, you will become nonlinear. Linearity, you define it as you put an input sinusoid, you get an output sinusoid. Right? Now you start clipping. Now automatically, if you clip, you can still extract out the fundamental of that clipped waveform. It will still give you a fundamental output signal. Okay, but now you will also get harmonics. And remember, this is going out into the antenna. Imagine you're operating at 2.4 gigahertz. There is something else operating at 4.8, right? You'll now be putting out junk at 4.8 gigahertz. You can't afford to do that. So you will have a filtering requirement. So what you can do, you can use a nonlinear PA. Use a filter. Okay, so this will give you F0 plus harmonics. So you put in F0, you get out F0 plus harmonics, you will need a filter. Okay, and then this can go to the antenna. You understand? Otherwise it can't. You can't put out junk. Now that filter can be explicit, it can be built into the matching network, all of that. Right? Now you understand. You can build the matching network such that it filters. Antenna will do some amount of filtering. Antenna is not like super broadband. Okay. Everything put together, you will need to meet the emission specs. Okay, for the power amplifier. Power amplifier cannot put out junk. There is some emission specs. One of the classes I had actually talked about a spectral mask and so on. You remember that, right? Yeah, ACLR and so on. I told you, you can't put out outside. You are killing out other people, right? Your adjacent channel, alternate channel, you can't put out junk. Similarly, if you go far enough out, you can't put out junk for other bands also. You can just extend it out. Now, it is possible to build such kind of PAs, but obviously, if you take a nonlinear PA and try to give it a modulated signal, your ACLR will get worse and worse as you start clipping more and more of the signal. Okay? You start clipping more and more of the signal, ACLR will keep getting worse. Okay? That's a problem. So normally you can't use a nonlinear PA to do linear. You will also get EVM problems, right? In-band performance will also, beta rate will also go bad. The adjacent channel leakage will also get bad. Okay, so normally linear, if you have information in both amplitude and phase, you try to build a linear PA. Now, if you start reducing the conduction angle, okay, if you conduct between I'll call this theta c. Theta c is equal to 360 degrees. I'll call theta c the conduction angle. This is called class AB operation. Primarily because if theta c was exactly equal to 180 degrees, this is called class B operation. Okay. And now what is theta c is equal to 180 degrees? The transistor actually conducts only half the cycle. So you get one half of the sinusoid, the other half of the sinusoid is completely clipped. I hope you see that. Correct? If theta c is less than 180 degrees, you can call this class C operation. Yes? Okay? And of course, class C operation covers it all the way to 0, almost 0. Okay? Now, how do you take a linear PA, the structure that we have built, I want to convert it into class B PA. How do I do that? The minute you do push-pull configuration, you can't, your output is not biased at VDD, you can't swing so much. Remember the class, so he's talking about a push-pull configuration coming from the, I guess low frequency amplifiers such as audio amplifiers, etc. Right? You can design the same thing, but not so easily. Okay? Technically, if you bias the inverter carefully, that can act as a in push-pull configuration. You remember the inverter, right? Let's go back to the inverter. If I take my inverter, I can bias, I cannot use it directly like this, as biased like this. The way it's biased, it is linear. But I can change the biasing of this to make sure that NMOS conducts half the cycle, PMOS conducts half the cycle. I can do that. Okay? I will give that as a homework. I'll tell you how to make RPA into a class B. You will automatically be able to extend it to the inverter also. But let us say I want to make this here. Okay, how will I do it? I am going to dispense now with all the input matching, output matching, etc. I am just going to dispense with the cascode. Matching network, etc. to take the simplest possible PA and then explain it. Sorry. This is the simplest possible configuration, right? We started off with. I'm not showing anything else. Okay, I'm going to use this as my template. I want to, this of course depends on the choice of I bias, correct? I want to bias it such that the conduction angle is 180 degrees. What should I have to do? Huh? At the threshold between triode and saturation. Which bias? The drain bias is VDD, correct? The triode region error, is very far away. At the threshold between cutoff. So remember, what is the gate voltage? Is basically VB plus sin omega t, correct? So if I were to plot this, I have something like this. Okay, this is Vs, capital Vs. Now, if I start reducing, correct, if I start reducing VB, remember we have designed it for class A operation such that the device always cuts off, which means that this total VG is always greater than VT. Okay, for class A, okay, for full cycle. Now if I start reducing VB, it will start clipping. I reduce VB to VT, then whenever input is in the positive half cycle, device will conduct. Whenever it's a negative half cycle, it won't conduct. Okay, so If I do this, I'll get class B operation. Does it make sense? If I reduce this below Vt, I'll get class C operation. That should also be straightforward. Okay, any questions? Now everything has to do with the biasing of the device. Okay, all these classes of operation have to do with the biasing of the device and nothing else. Okay, now these are the basic classes. There are now modifications of these classes because now you start putting out junk harmonics. You want to improve efficiency, right? But the minute you start going to class B, right, you start operating the transistor as a switch effectively. Okay, now you can imagine that my information is carried only in the phase, not in the amplitude, right? I want to operate it as a switch. Okay, so there is a more specialized configuration called class E PA, where remember you are going to operate it as a switch, right? Now go back to the efficiency of the PA. Okay, remember that the efficiency of the PA happens, forget about input matching, output matching for a moment. You are taking bias current from the supply and you're sending signal current into the load, correct? Now we wrote down an expression for efficiency. Let me actually show that here for the drain efficiency. Now let us take a look at this circuit in a little bit more detail. Where does in the original PA, where you had an efficiency of 50%, where did the other 50% get dissipated? Where?
Yeah, assumed it to be sinusoidal, and so.
No. What I'm asking is, I go back to my original PA. Okay, where is my? I'll go back to what I had here. Correct? What I had here. We said that the maximum efficiency is 50%. Correct? So you're drawing half the power from the supply. I mean, you're drawing power of P from the supply. P by 2 goes to the load. What happens to the other P by 2? It needs to be dissipated, correct? Where does it get dissipated? Huh? In the MOSFET, of course. So the MOSFET power dissipation, assume input is in capacitive. MOSFET power dissipation is simply ID times VDS. Okay, so I didn't explicitly mention that, but I think all of you know this, right? So the additional power goes into the MOSFET, where in M1 has average value of right. Or maybe I shouldn't write it like this. I'll just write it as, what is the best way to write it? Can I write it like this? VD RMS times ID RMS. Should be okay? It operates, this is the power. Okay. Now, I'm going to take this guy. Okay. I'm going to make the MOSFET like a switch, right? Because the input is biased at VT. When it's positive, it's high, otherwise low. Now, if I have imagine I removed the MOSFET and had an ideal switch. What is the power dissipated in an ideal switch? It's 0. Okay, because when it is on, the voltage across it is 0, because even though it can conduct a lot of current. When it is off, it has a lot of voltage but 0 current. Okay, so now I am going to do this such that I am going to modify. So I need extra circuitry, okay, to do this. I am not going to show it. So Passive circuits, not active circuits. The minute you add an active circuit, you have compromised the thing. Okay. Passive circuits, I'll say LC. So that, okay. So move this here so that I have more space. When VDS is positive, I am going to make sure ID is 0, and when ID is greater than 0, 0. That's what I am going to try to do. In other words, I'll show it like this. Let us say I take VD. Okay. Obviously, the actual waveform I'll get maybe I originally planned it such that I get a half sinusoid, right? And then I put a harmonic filter. But now I'm going to modify the waveforms, because remember that the switch will have an on time, finite off time, etc. For an ideal switch, there is no problem. Now what I'm going to do, the class E PA is specialized circuit where for a real MOSFET or for a real transistor, the overlap times between the current and the voltage, okay, is as small as possible. Okay, so I'll show it like this. So something like this. I'm going to try to reduce the overlap time when VD is large and ID is large. If I do this, I'll get maximum possible efficiency. Does it make sense? So this is time axis, of course. Okay. Okay. So now there is also, this is a specialized PA for switching power amplifiers. There is a class D for audio amplifiers. Okay. There is a class F for RF power amplifiers. So there are a lot more classes. Okay. I'll just kind of, there is a class D, there is a class F, class G, there is a class D RF power amplifier. There is something called an inverse class D PA. Now this thing is, you can imagine, it's a vast subject by itself. We are not going there. Okay. So I think linear PA is more relevant to the, I guess, the aim of this course, because going forward, majority of high data rate communication will end up having information at both amplitude and phase. Therefore, you will need a linear PA coming out of the CMOS chip to drive the off chip. The power levels are high enough such that you can't even imagine driving it with CMOS, but you want to put out just a few milliwatts of power. Okay. Any questions? Okay. So in that case, I'll stop here. I think that kind of ends the PA lectures.